Okay, so let's dive into this source material on artificial intelligence. We've got a lot to unpack here. Histories, definitions, the actual blueprints.
Right.
And our mission really is to get to the core of it. I saw this one definition I loved: AI as man-made thinking power.
That's a great way to put it. It's about creating machines that can learn and reason and, exhibit human-like skills without us having to code every single step.
Exactly.
But if you look at the source material, the goals were um, pretty grand from the start.
Understatement of the year.
I mean, the ultimate aim is replicating human intelligence. But on a practical level, it's about solving these really knowledge-intensive tasks. Things like planning a complex surgery or even playing chess at a high level.
It's interesting, though, that this ambition isn't new. Our sources mention Greek myths with, like, mechanical men. The idea has been around forever.
For millennia, yeah. But the capability, the actual technology, that really only started to catch up in the 1950s.
That's Alan Turing, right?
That's Turing. In 1950, he lays down the whole theoretical groundwork with the Turing test. But the official birth of the field, where it actually got its name, that was the 1956 Dartmouth Conference.
Where John McCarthy coined the term artificial intelligence.
The term itself. And that kicked off the so-called golden years.
Followed by the not-so-golden AI winters. A few of them, actually.
A few of them. Yeah, the hype got way ahead of the technology and the funding just dried up. But then the resurgence was impossible to ignore.
You mean like IBM's Deep Blue in '97 beating the world chess champion?
That was a huge milestone. But I think the even bigger one was IBM Watson winning Jeopardy in 2011.
Oh, absolutely. Because that wasn't just about calculation. It was about understanding natural language.
The nuance, the puns, the complexity, it was a massive leap. But to get to that point, they first had to solve a really fundamental problem.
How does a machine even start to look for an answer in, like, a sea of possibilities?
Exactly. And that brings us to these core mechanics.
Yeah.
You have what are called problem-solving agents. And they rely on search algorithms to find a path from a start state to a goal state.
And there's a huge difference in how they search, which is critical.
A critical distinction.
Yeah.
You have what's called uninformed search. You can just call it blind search.
Because it has no idea where it's going.
Not at all. Think of it as pure brute force. It's trying every single possible path until it stumbles on the solution. It'll get there eventually, but the computational cost can be just enormous.
So that's where informed search comes in. It's the smarter, more efficient way.
It is. It's also called heuristic search because it uses a heuristic, kind of educated guess or a rule of thumb to guide the search. An algorithm like A-star search, for instance, estimates how close it is to the goal.
So it's not just guessing blindly, it's making a smart bet on which path looks the most promising.
Precisely. You might not get the absolute perfect solution every time, but you get a very good solution in a reasonable amount of time. And for the real world, that's the trade-off you have to make.
Okay, so that's searching, but AI also has to reason.
Right, it needs to draw conclusions. And for that, we have inference engines that apply logical rules. The most basic one is modus ponens. If A is true, and we know A implies B, well then B must be true.
And the direction you apply that logic changes everything. Let's start with forward chaining.
Okay, so forward chaining is data-driven. You start with the facts, the data, and you move forward to see what conclusion you can extract.
Like a doctor diagnosing a patient. You start with the symptoms, the data, and you work your way toward a likely illness.
That's a perfect analogy. And the opposite of that is backward chaining, which is goal-driven.
So you start with the conclusion you want to prove.
You start with the goal, yeah, and you work backward to see if all the facts needed to support it are actually there. A troubleshooting system does this. It might start with the goal, the internet is down, and work backward to check, is the modem on? Is the router plugged in?
So when we talk about all this search, logic, chaining, this isn't some abstract theory.
Not at all.
This is the logic that's running the Roomba, cleaning your floor. It's the engine behind your Netflix recommendations. It's in self-driving cars.
It is everywhere.
Yeah.
But as you think about how these systems work in the real world, you hit the limits of the kind of logic we've been discussing. That's all deductive reasoning, where the facts guarantee the conclusion.
But the real world isn't so certain.
Far from it. And the source material brings up this much more complex challenge, something called non-monotonic reasoning.
And what's that?
That's a system where adding just one new piece of information can completely invalidate a conclusion you already made. So you might reason, Pitty is a bird, therefore Pitty can fly. Makes sense.
Sure.
But then you learn a new fact. Pitty is a penguin. Now your original conclusion, which was perfectly logical is overturned. For any system that has to operate in our complex, changing world like a robot navigating a room, mastering that ability to update and even throw out prior assumptions is, well, that's the real frontier of intelligence. Something to think about.